Okay, here we are. So I'm recording this session, and my plan is to record all our sessions together. And that way, if for any reason you have to miss a class, there'll be a recording of what went on so you can catch up that way. Or if there's just something that you want to look at again, it will be recorded. And I will post links to these in Eraser, our Eraser page, down in the bookmarks section. And I believe I posted a video of our Tuesday session there already. I'm fairly certain I did that, but we can check after class. All right, so resuming. We often write functions as equations. That's extremely useful. Functions can be written as equations, but not all equations are functions. So there's an equation, y squared equals x, but it's not a function. And here's the deal. I'll just label it bad. Using function notation, if f of x maps, if f maps x onto y1 and onto y2, it's not a function. Now, there are lots of different ways that people say this, but if you can, maybe it's easiest if you can remember this. To be a function, f has to take x into something uniquely. It can't take it into two things. So let's graph this equation that I've pictured for you right there. Now, we could do that using Desmos, and we'll use Desmos in a bit. But for right now, let me just remind you that that's going to be a parabola, and it's going to have this little piece right here is called the vertex. It's going to have the vertex at 0, and that's a sketch, of course. It's going to look something like that. That's an x-axis, and that's a y-axis. And if I would look at some value for x here, if I would look at x as x equal 4, then I see that the function, using graphic reasoning, maps that 4 onto this dot right there, but it also maps it onto that dot right there. So in this picture, f is sending 4 into two different things, and that makes it not a function. So maybe that's enough to say about that for right now. Oh, no, this is one other thing I wanted to say. If you have a graph, is the graph a function? And a way we use when we're dealing with graphs to tell if we've got a function or not is to use the vertical line test. And so if I can draw a vertical line that cuts the graph more than once, this vertical line in the orange cuts the graph there, and it cuts it there, then the graph is not a function. And what I said, be careful, I said, if I can draw any vertical line that cuts the function more than once, well, I could draw a vertical line over here that does not cut the function more than once. That doesn't mean anything. The question is it possible for me to draw a vertical line that cuts the function more than once? And so as another example, just to be sure that's clear, we could have a function that looks like, not a function, but a graph that looks like that. That's kind of a strange looking graph, but strange is okay. If I draw a vertical line out here, it cuts the graph in exactly one place. Here's a graph that cuts in exactly one place. And here's a vertical line that cuts in exactly one place. So does that indicate that orange is a function? No, it doesn't, because I can also draw a vertical line right here that cuts the curve in 1, 2, 3, more than one places. So that's not a function. So that's the vertical line test. And let's go ahead and work some problems out of our text. And the problems that I've selected for us to work together today are fundamental to working some calculus problems about business situations. So let's go to page You don't have to physically go to page 14 right now, but the problem we're going to work is off of page 14, and it's number 86. And so we're all on the same page. I'm going to read that problem to you. Let me grab my book. And problem 86 says, a company manufactures notebook computers. Its marketing research department, using statistical techniques, collected data shown in table 9. We'll look at table 9 in just a second, where P stands for the wholesale price per computer at which X thousand computers can be sold. All right, that's enough for us right now. Think about this, because so much of what you study in college you already know. If I'm selling something like a laptop computer, if I've got 10 of them to offer for sale, then it's a scarce commodity, and so the prices have to be higher than if I've got 1 million of them that I dump on the market. Then it's not scarce at all, and so the price is going to fall, and you already know that. Now, to quantify that, people use equations in business courses called price demand equations. And very often those are just given, but where does that come from? This says that if I'm have X is how many computers I'm selling. If I've manufactured 8,000 of those computers, the problem says that if I manufacture 8,000, $1,520 per computer. Now we're going to use the units of thousands. Just because it's a little easier to scale that to thousands. But the thing I wanted to just touch on real quick is, where does this price demand equation come from? It seems kind of artificial to give you the equation if I can't tell you where that equation came from. And where it comes from is a situation very much like in this problem, where I have a research department that goes out and sees what other computers are selling for and how many are available. And they may do market surveys, and they just do their due diligence, and they come up with a set of price points for me. And let me show you what that might look like. And I'm going to share a different screen. We're going to go to Desmos for just a second. All right, do you see Desmos? Okay. Now this is at desmos.com, and it's a graphing calculator. It will work on your iPhone. It will work on your Android phone. It'll work on Macs. It just works on everything. And it's really a nice utility. It will serve us well. You can start an account with Desmos, but you don't need to. You can use it as is. The advantage to having an account is that you can save things if you have an account. It's free if you want an account. You can save things. And so I have an account because I often do things I want you to see the night before and then just save them. So here's the table out of the book. And I entered that by going over here to the plus, add an item, and I selected a table. So I was able to add a table. And I copied this right out of the book. The book says if I have 1,000 units that I'm going to offer, I can expect to get $1,940 a piece for them. If I only offer 1,000, that's my price point. But if I offer, the next number is 8. If I offer 8,000, my price is likely to fall to $1,520. And you can see this either on the screen or in your book. I have a pair for 16,000, 21,000, and 25,000. So then the book says that the company used some kind of magic and came up with an equation. Well, what they did was a regression. Let's look at these points. And anytime you have data, it's always a good idea to use data. Now I can turn the graphing of these points on and off by clicking on this little colored ball there. Now they would be on, but I don't see them. Why don't I see them? Because the window I have into the XY plane goes from, it looks like from 0 to about 80 on the vertical axis and from 0 to 7 on the horizontal axis. It kind of misses all the data points, doesn't it? I need to adjust that window. And if I'm making big adjustments on the window, I'm going to come over to the wrench, and here's my x-axis. And I want my x-axis to be, what does it look like I'm interested in on the x-axis? Well, these numbers go from 1 to 25. And so why on the x-axis don't we look at 0 to 30? It looks like that would cover the part of the x-axis I'm interested in. And what about the vertical axis? Well, they go from 500 to 2,000. It's not a good idea usually to start graphs at 500 if they're representing quantitative things that we're interested in. That's called a non-zero based graph, and it can sometimes give you misleading visual images. So I'm going to make y go from 0 to 2,000. You know, as soon as I did that, I got green dots. What are they? The ordered pairs out of this table. So here's my green dots. Now, what I'd like to have is an equation that gives me a graph that goes through or at least close to these green dots. Now, what kind of a pattern do you visualize here as you look at the placement of those dots? That looks like a, kind of looks like I could draw a straight line through those, doesn't it? Looks like a linear pattern. So one of the things I can do is ask Desmos to give me an equation for a linear function that goes through these points. Now, come over here, if you will. The form of a linear function is y equal ax plus b. You may have learned that in high school as y equal mx plus b, where m is the slope. I'm just calling it a today. But a is the slope and b is the intercept, or where the line crosses the vertical axis. I see that a line that fits these points really well is going to cross the vertical axis somewhere up here above 2,000. And what's the slope? Well, I could figure that, but the slope is going to have to be negative, right? Because a line that goes through these points is going to go from upper left to lower right. And so the slope would be negative. So I expect all of those things. Well, I'm going to tell Desmos to find me the line that fits these points best. Best in the sense that I want the line that minimizes the vertical distance between the line and the points itself. And here's how I tell Desmos to do that. I say y1, I'm just going to retype this. Let me get rid of this. You know, we can come down here, and I'm going to say my first value of y1, and instead of saying equals, because I'm not writing an equation, I'm writing a suggestion for the form that I want an equation to take, equals a times x1 plus b. Now, you know, Desmos is so fast, it's already filled in something for me here, but let's look at what these components are. This comes from the table that I've got, the ordered pairs. Notice that we've called the y's y1s. and the X's X1s. If I had another table, Desmos would call those Y2, X2 and Y2. If I had another table, it'd be X3, Y3. So that's why we've used Y1 when we wrote this template down here. I didn't use equals because the tilde is a symbol that I want Desmos to calculate the value of A and B for me. And did Desmos do that? Well, I see that A is -60 and B is 2000. So Desmos did that. And not only that, it graphed it for me. Now, how good is that graph? Well, that's pretty darn good. I mean, if this was real market survey and not a problem in the back of the book, I would think that my marketing people probably didn't survey. I would think they probably made these numbers up because it's too perfect. I'm always skeptical when things are too perfect. You should be too. But, you know, this equation that we've just discovered, man, it fits these values perfectly. So, okay, maybe that's really what happened. Maybe we got lucky. So now we know the equation here, and this is a price demand equation. So if I would look on the horizontal axis, let's see, that's the X's, so that's how much I'm manufacturing. If I would decide that what I'm going to manufacture is 20,000 of these laptop computers, what price could I expect? Well, just come up and over, and I could expect, looks like $850, $900 per unit. Now that's not real precise, is it? In Desmos, I can get a tiny bit more precise just using the graph by taking my pencil cursor here and clicking on the equation. And the point that I just clicked is 19.95 and 8.03. And let's see if I can move that. Boy, I slid that just a little bit and got it perfect, didn't I? That tells me that at 20,000 units, remember the units are thousands, at 20,000 units, I could expect $800 per unit. Okay. So now we've read the first part of the problem out of the textbook, and they gave us the equation. They said, using special analytical techniques, an analyst produced the following price demand function to model the data. And here's the price demand function. P of X, P is the price, is equal to 2000 minus 60X. 2000 minus 60X. Notice that's exactly what we discovered ourselves. Here's the 2000. And then the A, the slope is minus 60, 2000 minus 60X. So that's exactly what we got. And we used Desmos. We didn't have to rely upon some unnamed analyst to do that for us. A says, plot the data points in table 9. Well, look here they are. They're already plotted. I'm going to turn this off so you can see again the data points. Plot the data points. We've done that part. And then B says, no, it's still A. Plot the data points, sketch the graph of the price demand function. Well, we can do a little better than sketching the graph. We can draw it very precisely using Desmos here again. What would be the estimated price per computer for a demand of 11,000 computers or for a demand of 18,000 computers? What would be the price point for 11,000? We know the equation, so we can solve that numerically, but we can also solve it graphically. 11,000 is going to be over about here. So let's get up on the graph and let's see if we can get this thing to 11. Sometimes it jumps around too much, but there we are. At 11,000 units, the price would be $13.40. And what about 18,000 units? 18,000 units would be right in here somewhere, moving toward 18. $920. So that's kind of the easy way to do that. I'm going to share a different screen with you. Let's do that analytically. And if we do that analytically, remember we found that P of X is equal to 2000 minus 60X. So we were doing it graphically, but we can do it algebraically also. And what would be P of 11? Now, why am I writing 11, not 11,000? Because we use the units thousands. And so P of 11 would be what? It would be 2000 minus 60 times 11 would be equal. Well, we're going to discover where we saved our calculator to. And we're going to say 2000 minus 60 times 11, 1340, which you may remember from looking at the graph. And P of 18, well, it'd be 2000 minus 60 times 18 would be 2000 minus 60 times 18, 920, which you may remember from looking at the graph. And if you want, this is dollar amounts and would look like that. And what's the interpretation of this? I want to get the negative in here too. This negative 60, what did you call that in your algebra course? You call that the slope, didn't you? Yeah, in a linear equation you can recognize because the variable x is to the first power only. In a linear equation, the coefficient of x is called the slope. So the slope equal to negative 60, that implies, since it's negative, each new 1,000 computers reduces price by $60. So it's going to be important to us when we start studying differential calculus that we have a good interpretation of that slope, because notice that the slope really is a rate, isn't it? It tells me that I'm going to reduce by the ratio 60/1 as I produce more thousands of computers. So that slope is the first ratio and the first differential that we'll be playing with, but that comes in another day or two. All right, so let me see where we are here. My goodness, we've done all of that. Now that we know something about the price demand, and we know where the price demand equation came from, P of X is equal to 2000 minus 60X. What can you tell me about the revenue that this company can expect as it manufactures more or less computers? I mean, I guess, how would the company decide whether to make 1,000 computers or 10,000 computers? Kind of flip coins or just randomly, ask your grandson how many you'd ought to make, or maybe look at revenue, huh? You'd probably look at the revenue, and that's going to inform my decision. Well, do we have enough information here to know anything about the revenue? Can we project the revenue for this company? And what is the revenue? I mean, just think, if you're going to have a lemonade stand in the front yard, what's the revenue going to be?
The price of the lemonade times the amount that you sold.
All right. So the revenue is going to be how many units did you sell times the price per unit. And that's all revenue is, right? That's pretty simple. That's all it is. Well, are we in a position now to forecast the revenue? Let's make it a function R of X for this company. Well, if they manufacture X thousand units, what can they expect the price to be? Oh, that's why we have a price demand function. They can expect the price to be P of X, right? That's what the price demand function tells you. So now let's do just some algebra. This is just high school algebra, but what is P of X? I'll even put it in big brackets so we don't lose sight of the fact that what we're writing here is P of X, but it's 2000 minus 60 times X. Now that is perfectly correct. But if we're going to be using the revenue function, it's probably worthwhile to clean this up a little bit. So by clean it up, I mean, I could distribute this multiplication right here and get an equivalent, but maybe a little simpler expression that would look like that. So the revenue is going to be 2000x minus 60x squared. So what if I decide that I'm going to manufacture and sell 5,000 of these computers? Now that would be a 5 in here, right? Because our units are thousands. Then we would expect the revenue to be 2,000 times 5 minus 60 times 5 squared. Might as well figure out what that's going to be since we've got the equation and we've got a calculator. So that's going to be 2,000 times 5 minus 60 times 5 squared is 8500. And that would be dollars, 8,500. I think we might as well see what the revenue situation is looking like. And to do that, why don't we graph the revenue function? Now, here's the revenue function. And you may remember, and if you don't, no harm done. But you may remember that we would call that a quadratic equation because the independent variable X is raised to the second power, and that's the highest power of the variable is the second power. So that makes that a quadratic equation, and all quadratic equations graph as parabolas. Sometimes they open up, sometimes they open down, but they all graph as parabolas. You can also tell which way they're going to open by the sign of the coefficient of the x squared, but we don't really need that right this second. Let's stop sharing this screen and start sharing our Desmos again and do some graphing. I'll move you over to the right again. Now, this is the revenue function that we discovered. The revenue is equal to how many units we move times what we can expect will be paid for those units. And this is just our price demand function. And we clean this up and we know another form for it, but Desmos will do that for us also. So I'm going to turn that on, just a click on and off, and it's going to be in black. And here it is, and here it is. Not real convenient because my window isn't right. So let's clean that up. And what would we want this window to be? Well, I can see again that I would want X to be just about where it is. I would want X to be between maybe 0 and, let's just say 50. But Y now, I want to run between 0 and, the beautiful thing about not sketching by hand and using something like Desmos is you can fiddle with it. You don't have much invested. So I kind of guessed here that Y would work for us if it was between 0 and 50,000. Well, yeah, it works, but really all I need is about 20,000. So it doesn't cost me much. That's a better picture. All right. So what is this? This is our revenue. This is our revenue function. And it is ordered pairs that tell me if I manufacture 5,000 units, that's what this 5 would stand for. Let's come up here and just kind of click on that. Then I would expect a revenue of $8,444, since that's a 0.9. We'll just round it to 44. $8,444. What's the max revenue that I could expect? Where is revenue the highest? You know, now that we got a picture of that revenue function, it's pretty clear that this point right up here is where revenue is going to be the highest, isn't it? So would you make 10,000 of these computers? Would that be your choice? Why not? Well, because I can get better revenue, can't I? If I would come up here and make about 16,700 computers, I could get better revenue. Now, what if I make more than the 16,700? That'd move my X over this way, and my revenue is decreasing. Flood the market, you know, it becomes too common, people won't pay as much for it. So we learned something by just looking at the graph here. The revenue function, we said, is going to be the number of units times the price per unit. And then we can work that out algebraically, or we can ask Desmos to work it out, and we get a picture of the revenue function. And we can see where revenue is maximized by just looking at the graph. Now, I've got another question for you. And I'll point out one more thing to you also. In Desmos, if you have a graph and click on the graph, then I get a dot that appears here, and a dot that appears here, and a dot that appears here. And that's something that Desmos calls the interesting points. Now, depending upon the shape of the graph, which points are interesting will change. But right now, this is just a parabola. So what would be interesting about a parabola? Well, probably where it crosses the horizontal axis. So that's these 2 points, and the maximum, or the vertex. So you don't have to go shopping for these. If you just click the graph, Desmos will give you those. It's just a well thought out program, very user friendly. Jonathan, you have a question.
So another thing I think you forgot to point out is that the intersection. Is that an interesting point? The intersection with the other graph?
Oh, well, yeah, I think it would be, huh? Since I've got 2 of them, and I've got that dot also. And there are 2 dots on there because it intersects at 2 points. It intersects at 1 and at 33 1/3. So those would be interesting points. Where 2 graphs intersect, Desmos says that's an interesting point. Now, this is the price demand function. So I don't know that there's a practical interpretation for us for these 2 points. But anytime two graphs intersect, Desmos thinks that that's potentially pretty interesting. So maybe we don't need those right now. In fact, let's get all sophisticated here and get that out of our picture. Now this is just revenue. This is my revenue. And we said the revenue is max right here. But the question I want to ask next is revenue the same as profit? And Emily, who is voted most apt to answer my questions, says no. Other people can participate in this discussion, but Emily, why is revenue and profit not the same?
Revenue is what you make off just selling the product. You have to take to find profit. You have to take into account the cost of producing that product and subtract it.
Well put. Of course, it costs me something to make that product that I'm selling. So we need to explore the cost function. Well, the next problem in the textbook says, suppose that, again, my financial people in this company have looked at this computer and they would look at what components I'm using and how long it takes to put the pieces together and what the advertising budget is. And they come up with and give me an estimate of what the cost is going to be. Now, rather than to go back to the whiteboard, I typed in what they told me right here in Desmos. And so let's save a minute and just look at the cost function here in Desmos. So what they've told me is that C of X, that is the cost if I produce X units, is going to be 4,000 plus 500X. 4,000 plus 500 times the number of units that I'm producing. Now, a cost function has got a couple components here. The 4,000 is called, you may not know this, but if you know the vocabulary, share it with me. What would the 4,000 be called? It's okay.
Would it be a constant variable?
Yeah, it's the fixed cost. That's the fixed cost. Fixed cost would reflect rent on the plant and maybe some insurance that I'm going to have to pay, whether I manufacture or not. So those are the fixed cost. And then the 500X, that represents variable cost. So the more units I produce, the more it costs because I've got to have the raw materials that go into that unit, whether that's steel or plastic or computer chips. I've got more labor involved if I'm manufacturing. And so those are variable costs. So there's two components to cost, the fixed cost and the variable cost. Now, our finance department has given us our cost function. So let's go ahead and graph that cost function and see what that looks like. And that is what it looks like. And I have forgotten now who said, wouldn't it be interesting to know where these two functions cross? And it would be. And Desmos has given us the intersections here. Now, what would be the interpretation of the intersection of those 2 points?
Dr. Simon, I was going to go and just take a blank guess. It could be a break-even point or a, somewhere where something's neutralized, I guess. I was going to take a guess.
Well, that's an excellent guess. It would be the break-even points. Because what's happening at this point right here where the two cross, this is my cost function, right? It tells me what it's going to cost to produce X units. This is my revenue function. That tells me what I can expect to bring in if I produce X functions. And at this point, those two are equal. That's why the graphs cross. That means my cost is equal to my revenue. So this is a break-even point. Now, because my revenue function is a quadratic, I've got another break-even point here. So I could also manufacture 22,000 computers. Now my revenue would be considerably higher than it was down here, but so are my costs. And my cost and my revenue at this point would be the same. And again, that's a break even. So where do I want to manufacture? What's the domain here on my how many units to manufacture? Well, it's going to be between these two dots, isn't it? It's going to be between 3,000 units and 22,000 units. Because if I manufacture less than 3,000 on my revenues, I would be over here, and my revenues would be less than my cost. What does that mean? That means I'm losing money, doesn't it? Or I would be operating on this part of my revenue curve, but again, my revenues are less than my cost over here. That's not where I want to be. I can't run a business that way. Now, what is the profit? Emily told us that the profit was going to be the revenue, but you got to take away the cost. So notice that the vertical distance, anywhere I want to operate between these two dots, but anywhere between those two dots, the vertical distance between the blue and the black, that represents profit. We decided that the profit function would be the revenue function minus the cost function. Does it matter what order I put these in? Could I swap those around? Would it work as well? If I swapped them around, I would have the negative of the profit function. So the order does really matter here. The revenue I want to be greater than the cost. So that's going to make the difference positive. Now, we can go a little further into this is absolutely correct, but we can also write down, since I know that my revenue function is 2,000 x minus 60 x squared. Where did I get that from? I got that from right here. That's the revenue function minus the cost. And the cost function, you got to be careful of your algebra here. The cost function from the textbook was fixed cost of $4,000 and variable cost of $500 per unit. I mean, we're reviewing, so it's okay if I stop and tell you to be careful here with this subtraction sign, the subtraction right here, because it subtracts this whole thing. So don't get in a hurry and write minus 4,000 plus 500x. I mean, that's going to be a tiny, tiny mistake here, but it's going to make everything wrong after this. So use parentheses and just be patient. Go slow. We're not in a race here. Let's clean this up just a little bit more. My profit is going to be 2,000x minus 60x squared minus 4,000 plus 500x. Let's keep cleaning equals, because I've got a 500x and a 2,000x. I'm waiting for somebody to yell at me.
Isn't it supposed to be negative 500x?
Thank you. That was Erica. Yeah, I made a mistake right here. Because why? Remember, the algebra rule says that when you have an expression that is enclosed in parentheses, to drop the parentheses, if the expression is preceded by a negative sign, you have to change every sign within. And I changed the first one, but I didn't change the second one. Okay. Now, when I make a mistake, tell me. And I'm going to tell you, if I make a mistake, I did it on purpose to see if you were watching. That's not true. I make a lot of mistakes just because I make mistakes like you do, but I'm going to tell you it's because I wanted to see if you were watching. So what have I got here? 2,000x minus 500 would be 1,500x minus 60x squared minus 4,000. So there's my profit function. What kind of a graph would that profit function have? What would the shape be?
Would it be, I'm just going to go on a long shot and say, would it be two parabolas or at least one? It would be two parabolas?
One. It would be
One,
it would be
one,
one.
okay.
But you're right, Jonathan. It's going to be a parabola. And you know that because look at it, it's a quadratic equation, right? The independent variable is x, and the highest power of the independent variable is 2, is squared. And all quadratic functions graph as parabolas. Let's go back to Desmos and let's graph this profit function on the same axes that we've been playing with. So I'll look at that. I can write on there. So I got to stop the screen share there, but start the screen share here and move your pretty pictures over there. Do you remember this function? P equal 1500x minus 60x squared minus 4,000. That's exactly what we calculated a minute ago. I did this before I went to bed last night to have it ready for you and turned it off, but now I'm going to turn it back on. And the red, and see, you can go from what's this ball out here? It's red, and that's what the function is here. The red is my profit function. Oh, there's numerous interesting things here. First of all, it may be a tiny bit hard to see, but let's pick a vertical line. Let's pick 10 right here. Then the value of my profit function at 10 is just about 5,000. It's 4953.65. But that would be exactly what you would get if you would take the value of revenue at 10, 14,000, and subtract the value of cost at 10, 9,000, then that's what the profit would be. So I can see the profit as the vertical distance here, but it's a little bit hard to really visualize that, except I can see the vertical distance is greater here than it is over here. Vertical distance, not so big over here, pretty big right here. It's easier to see it if we go ahead and graph the profit function. So the red is the profit function. The second thing that we can observe is, where is the profit max? It's going to be at this vertex, right? This is the profit. It's going to be max at this vertex. Now I could fish around and find that vertex, but that would be an interesting point. So if I just click my graph, there it popped up, and the vertex is at 12.5, which would be 12,500 units. I maximize my profit at 12,500 units. Where do I maximize my revenue? I maximize my revenue at 16,667 or 16,000 and 2/3 units. Should those be the same, you think? Because they're not the same. So if you think they should be, we made a mistake somewhere. Well, I'm thinking they're probably not the same, because there's more to figuring out what your profit is than figuring out where your revenue is maximized. I get the maximum revenue at 16,000 and 2/3 units, but it costs me a lot to produce those. I could produce fewer, 12,500, and the reduction in cost would make that more profitable than maximizing the revenue. So I will maximize my profit. And after all, that's what I'm after, not just revenue. I maximize my profit at 12,500 units. And that's what that series of 3 problems out of our textbook wanted us to start thinking about. So I hope you got something out of that. But I'm going to assign a set of problems like that. In fact, I've already posted them. I believe I did that last night. If not, I'll do it later this afternoon. 3 problems similar to these for you to work on. When you're doing your homework, certainly feel free to use these tools. Use Desmos, and you can take screenshots of these graphs and include them in your homework PDF. So I want you to use technology. Let me stop sharing Desmos and start sharing our whiteboard. Okay, again, just continuing with review. Same problem set. Let's look at problem 91. In problem 91, we've got a piece of cardboard, they say. And on one side, it's 12 inches. And on the other side, it's 8 inches. So it's an 8 by 12 piece of cardboard. Now, if I will cut corners out, cut squares, now those are all the same size square, although, you know, they may not look like it because I'm not a very good drawer. And then if I would fold along the dotted lines, I would wind up with an open box, right? Can you see that? So the question in problem 91 is, what's the volume of the open box in terms of the size of the square that you cut out? Well, now, what would you say the size of this square was? I mean, I would say that it is, if that's X, that would have to, it's a square, so that would be X also. So I would just say, you know, it's a square X on a side. So really what I want here, all the question is asking me about is, what's the volume as a function of X? How big that little square I snipped out is. Now, I would know the volume of this box if I knew this measurement, right? And this measurement. And that measurement. What is the volume of a box like that? What's the formula for that? Remember, this is review, so we probably asked that before, but you were probably much younger then.
Length times width times height.
Precisely right. Length times width times height. And so let's put this up here in our fun things to know and tell. Volume is equal to length times width times height. Now for this general box that we're drawing here, what are these values going to be? Length, width, height. What would be, this will be the length. What would that be?
2.
Would it be from here to here? Would that be the length?
No. Wait for the, you mean for the box right here, or for the cube, or mean for the rectangular prism? Which one?
Well, the answer is the same. So
Well,
I'm assuming that I went from here to here by just folding this piece up. This is gone. This is out. This is out. This is out. This is out, and I fold on this dotted line, fold here, fold here, fold here, and I get this.
It's 8.
Wouldn't it be 12 minus 2x?
Yeah, let's think about that. What would it be?
Mm,
I had 12, but I took away x, and then I took away another x. So all that's left would be 12 minus 2x, right? Now, if x was 2, then this would be 12 minus 4 would be 8. But we want it in general. So it'd be 12 minus 2x. What would this measurement be over on this side? Now, what is this side? This side is here to here, right? This was 8 inches. From here to here was 8 inches, but I cut out an x there and an x there. So what I'm left with here, same reasoning, would be 8 minus 2x. So this would be 8 minus 2x. How tall is this box? That'd be the height, the last one
X.
Wouldn't be just x.
would be just x. So now we're in a position to write the volume as a function of x, because we know that the volume is length times width times height. And so it's going to be the length we decided was going to be 12 minus 2x. Length times width, 8 minus 2x, times height, x. That is a correct answer. Depending on what we want to do with it, it may not be the most convenient form to have that answer in, but that is a correct answer. Now, how can I change the form? Well, these are indicated multiplications, right? So I could just carry out those multiplications and I would have the same answer, but in a form that I might like a bit better. And let's see, let's go ahead and do this. Now, I'm going to rely upon the fact that multiplication is a binary operation. That is, I can only multiply one thing by one thing. If I got 3 pieces I need to multiply, then I need to pick 2 of them and multiply those together first, and then multiply by the third. So I'm going to take these 2 big parentheses and just kind of get this out of the way. Now, you learned earlier how to, I don't mean earlier in this course, but in your life, how to multiply things that look like this. We call this what did you call that? You learned that in high school. I'm thinking all of you probably learned that. Multiply 2 binomials. You used a method that your instructor called FOIL. Is that right? And what does FOIL stand for? FOIL. First, outer, inner, last. I didn't learn FOIL. Y'all or the people that came before you taught me FOIL. I'd never heard of that before. When I went to high school, they said, just do it. But FOIL would be to multiply the first, that would be the 12 times the 8. So what's 12 times 8? Is it 96? First, outer. The outer would be 12 times 2x. And what about the sign? Be careful of the sign here. So this would be minus 24x. First, outer. Inner would be these 2. So this would be negative 2x and 8. So that would be negative 16x. And the last would be a negative 2x times a negative 2x would be a positive 4x squared. But we're not done. We still got this x over here. We haven't multiplied this x yet. All right. So now I guess cleaning up, I can see that I've got a negative 24x and a 16x that I could combine. And that's all the cleanup I can do inside the parentheses. And then I've got to multiply everything by X. Let me, in the interest of time, just kind of tell you that the result, and you can check me on this, is going to be 96X minus 40X squared plus 4X cubed.
I think
So
you're
that's-
correct.
Is that correct?
Yep, I think so.
Yeah, I think it is too. Thank you, Jonathan.
You're welcome.
That is the volume of the box that we create in terms of what we snip out of the corner. What kind of an equation would we call this?
It's a cube root, so it's going to be like a zigzag, right?
It's going to graph as a zigzag, and we're going to call it a cubic equation because
My bad. Sorry about that.
they're related words. I know what you mean. We're going to call it cubic because the independent variable X is raised to the third power. That's the highest power X is raised to. So that's going to be a cubic. And all cubic equations either look like that. Now I'm saying equation, or they look like that. Let me exaggerate this a little bit. Much prettier. Now those are cubic equations. This one would be a function. Try the vertical line test. If I draw any vertical line, I can cut that function at most once. Try the vertical line over here. Oops, wait a minute. 1, 2, 3 cuts. So if it plots like that, it's not a function. It is an equation. Plots like this, it's a function. In the time that we've got left, let's just zip back over to Desmos and let's graph this equation. Now, I've already got it in, but some of you will remember what that is. I won't, probably will forget. But let's go back to Desmos and let's clean up our screen by turning off things we're not using anymore. And V for volume. V, I didn't expand it here in Desmos. You can get lazy using Desmos because it'll do that multiplication for us. We just multiplied this out, but it's exactly the same thing if I let Desmos multiply it out. Let's go ahead and turn it on so we can see what the picture looks like. Now, it's above and it's below. I think I'd like to get a little better look at this piece in here. So what I'm really interested in would be between -5 and about 10, but I don't need to go too much on the vertical scale. This vertical scale is so big that I really can't see these squiggles in here very well. So let's set our window to -5 to 10. And maybe -10 to 20. That's not quite enough. So let's go -50 to 100. See, the nice thing about using technology is I didn't invest a whole lot of time in graphing that before I decided that my window wasn't really adequate. So just a flick and I can change that window. So this is the volume of the box. And really, this tells us quite a bit. It tells me that this would be the x-axis. That's what I snip out. And look, it looks like the green is the volume If I don't snip anything, I don't get any volume. 0, 0, right here where the cursor is. But as I snip bigger and bigger squares out of the corner, my volume goes uppity, 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 up. But when it gets to this point right here, that's one little over 1.5 inch squares, the volume starts to decrease again. And when I get down to 4, if I'm cutting a 4-inch square, my volume is 0. Does that make any sense? Well, we got a piece of cardboard that's 8 inches on a side, 8 by 12. If I cut a 4-inch square, what's the short side going to look like if I cut out an 8-inch square from the top and the bottom?
It's going to be 0.
It's going to be 0, and then the volume will be 0, won't it? So really, this tells me in a practical evaluation, the only squares I can cut are going to have to be between 0 and 4 inches. And 0 is going to give me no volume, and 4 is going to give me no volume. And the values in between will give me legitimate boxes with varying volume. But my best volume will be at 1.569. That'll give me the most volume that I can get. Well, we're going to quit here because of time. I have posted a few more problems for you. So be sure you get on those so that the next time we meet, if you have questions, that would be the time to ask them. Or come to my office hours on Monday. We've got office hours after you study all weekend. I know that's what you do with your weekends, right? Yeah. So after you study all weekend, Monday, if you've got questions, come to office hours or send me an email. Have a good weekend. Be safe, whatever you do, and I'll see you next week.
Have a good weekend.
Thank you. You too.